So we've discussed what values of L and ML are allowed depending on what value of N we're looking at. Now let's look at the shapes that are predicted by these quantum numbers. So for every single principal quantum number, 1, 2, 3, 4, 5, 6, 7, 8, etc., L equals 0 is a possibility. When L equals 0, that is the S subshell, and there is always one orbital in that subshell. S orbitals always have the same appearance. They look like a sphere. Now the difference between the S orbital in the first and the second and the third energy level primarily is the distance that the electron is from the nucleus. So the 1s orbital is going to be closer to the nucleus than the 2s orbital, which will be closer to the nucleus than the 3s orbital. So as we increase our energy level, the shape remains the same, but it becomes larger as that electron probability is further from the nucleus. Now, once we get to the second energy level and above, n equals 2, 3, 4, 5, 6, 7, 8, etc., we have L equals 1, or the p subshell, that is allowed. When we have the p subshell, there are 3 ml values, which means there are 3 orbitals always in the p subshell. And this is what these 3p orbitals look like. They look sort of like a peanut, if you will, and at the center is the nucleus. The difference between the p orbitals is their orientation around this Cartesian coordinate system. I'm going to bring another slide to kind of give you a close-up. We can think of the p orbital as being aligned on the x-axis, on the y-axis, or on the z-axis. So we call these orbitals the px, the py, and the pz. If we're talking about the second shell, then they would be the 2px, the 2py, the 2pz. Third shell, 3px, 3py, 3pz. Fourth, 4px, 4py, 4pz, etc. And this graphic B shows all 3 together as a composite. Typically, we tend to separate them so we can see clearly how the lobes of the orbital are oriented on the axis that the orbital is named after. So the p subshell always has 3 p orbitals, and they are oriented differently along the Cartesian coordinate system. Now if we look at the next subshell, which is L equals 2, that becomes allowed when n equals 3, or the third shell. We call that the D subshell. And there are 5 ml values, which means there are 5 d orbitals. And these are pictured here on this graphic. Let me just point out the colors are just for us to distinguish between them. Orbitals really don't have a color. Here are the 3d orbitals. And the 4d and the 5d would look the same. They would just be larger, further from the nucleus. And they are also named according to their orientation along the Cartesian coordinate system. So dxy has 4 lobes that are in between the x and the y axis. dxz has 4 lobes which are in between the x and the z axis. dyz has 4 lobes that are in between the y and the z axis. And dx squared minus y squared has the 4 lobes on the x and the y axis, while dz squared has 2 lobes on the z-axis and this little donut around its middle. So the 4d, the 5d, the 6d orbitals have the same shapes and orientation. They're just larger. So 4d would be further from the nucleus, 5d even further, etc. The f orbitals become allowed at the n equal 4 shell. And since there are 7 ml values when L equals 3, there are 7 f orbitals. And they have an even more complex appearance than the d orbitals. Most textbooks don't go over the f orbitals because they are more complex, but I just wanted to show you what they look like and also share with you a little simple tool that I use to remember the shapes. S for sphere, P for peanut, D for double peanut, except for the d z squared, and F for flower.